So let's use what we know about about integration rather of power series to find power series for the functions arctan x and ln of 1 plus x. So first let's do arctan x. The thing to observe here is that arctan x is equal to the integral of dx over 1 plus x squared, right? We we know that from earlier work. So now focus on this expression and notice how this looks like something we're going to be able to turn into, we're going to be able to rewrite in that form 1 over 1 minus box, where we're going to be able to use the geometric series expansion to get a power series for that function. So I'm going to rewrite this as 1 minus negative x squared. Agreed? Those are equivalent to each other. So we know now how to write this term as a power series, so that's going to be equal to the integral of the sum from n equals 0 to infinity of negative x squared to the n. And I actually need dx after that because we are integrating. So let's see, write this a little bit more cleanly. This is going to be n equals 0 to infinity of negative 1 to the n x to the 2n. So now all I have to do is just apply the normal rules for the normal power rule for integration to integrate this general term of the series. So this is going to be the sum from n equals 0 to infinity of negative 1 to the n. Remember, negative 1 is not a variable, so that doesn't in any way get affected by the integration rule. This is just for each term, for each value of n, this is just a constant. It's going to be either 1 or negative 1. This is where I apply the power rule. I'm going to increase the exponent by 1, so this is going to be x to the 2n plus 1. There's no parentheses around the n plus 1, by the way. I'm taking the exponent, which is 2n. There was just some even number, and I'm adding 1 to it. And then I divide by the new exponent, which is 2n plus 1. So that's the series, and we're almost done. Recall that we always have to add plus c because we could be getting any one of an infinite number of possible antiderivatives. The thing is that what we know is that we want this to actually equal the arctan function. So we just need one data point about what arctan equals. I'm going to use the fact that arctan of 0 is equal to 0. That's true. The angle whose tangent is 0 is in fact the angle at 0 radians. So what that means is that if I plug 0 into this series, I should get 0. As long as I've done that, as long as this gives 0, then I'll know that I don't have to add any constant. To get this to equal the arctan function. So what we can see is that we're going to have here, starting at n equals 0, we're going to have x to the 0 plus 1. That's x to the 1 over 1. And we'll see that we're only going to have positive powers of x in this series. It's going to be, the next one is going to be x to the x cubed, the next to the fifth, the next to the seventh. So we can see is that if I replace the x here with 0, I do in fact get the sum of the series is just 0. So that means that this series is going to give the correct arctangent of 0 without me having to add any constant. So this is in fact the answer. This is the series for arctan x. So now let's do something similar with ln 1 plus x, and the ln 1 plus x function actually comes up fairly frequently in the next couple of sections, so it's worth knowing what it is. So let's find that. Let's observe that ln of 1 plus x is equal to the antiderivative of dx over 1 plus x. I can certainly verify that if there's any question about it. I can say that the derivative of ln 1 plus x is equal to 1 over 1 plus x times the derivative of 1 plus x, which is 1. So in fact, I get to the expression after the integral sign if I differentiate that. So it's certainly correct to say that the antiderivative of ln of 1 plus x is just 1 over 1 plus x. So let me erase this so it doesn't get confusing. So this is going to be the integral of dx over 1 minus negative x, and that gives us the integral. I know how to write this expression as a series. That's going to be the integral of the sum from n equals 0 to infinity of negative x to the n. That's going to be the integral from n equals 0 to infinity of negative 1 to the n, x to the n. And I do the same thing that I did before. I'm just going to apply the power rule to that series. So that's going to be n equals 0 to infinity of negative 1 to the n times x to the n plus 1 over n plus 1. That's that's the series. So this is the series for ln of 1 plus x, like that. And you'll often see this series written in this form where we shift the index down by 1, so sorry, up by 1. So I'm going to start it at n equals 1 to infinity, since that's going to lead to a different positive or negative here. In other words, if I start the series at 1, then the first term would be negative, and we can see that I really wanted the first term to be positive, so I'm going to change this a little bit and write negative 1 to the n plus 1. In fact, let's make it more consistent. Let's say to the n minus 1, so you can see that I shift this up 1, and then I shift everything here down 1. So since I'm starting at 1 instead of 0, I don't need to add 1 to that exponent of x, and that just becomes x to the n over n. So this is another way to write the same series. If you want to convince yourself that these two series really are equivalent, the best thing to do is take out a piece of paper and just write the first four terms of each series. Start this one at 0 and write the first four terms. Start this one at 1 and write the first four terms, and you'll see they're identical. That's probably the best way to convince yourself that they're really the same. So here are the series for arctan x and ln of 1 plus x, and this is how we got to them, using this nifty new tool of being able to integrate and differentiate power series as if they were really the function, because they are. This is a bit of a teaser for the next section in the book. We're going to be talking about a much more general way to write a series that stands in for any function in a particular class of functions that we call the analytic functions.